right, let's start today by talking about how to simplify radicals, because this is going to be a skill that we need as we move into the quadratic formula later on in class. So simplifying radicals is something that you have previously learned, but it's also something that I feel like many students forget how to do because it's not something you use super often. So it's best practice in math to leave your answer in exact form, meaning not typing your square roots into the calculator and rounding it as a decimal. So it's best practice to simplify your radical and leave it in simplest form that way. So up at the top, I have all of the perfect squares listed from 1 through 12, meaning these are the numbers that have exact square roots. So if you have those numbers pop up, you'll be able to just take the immediate square root and move on with your life. But if not, then you're going to have to simplify it. I'm going to teach you one way, but actually I might teach you two ways. But there's a lot of different ways you could think about it. So if you're more comfortable with a different form of simplifying radicals, that's a-okay, as long as you can get it in simplest form. Okay, so the first example, we have square root of 36, which we know from the top and just from our knowledge that we've gained over the years, the answer to that is 6, because 6 times 6 equals 36. Okay, so the method that I'm going to show you to simplify radicals is going to be prime factorization. So I prefer the upside down birthday cake. You might like factor trees better, but to me, this takes up less space and it's quicker than making a tree and making all of your branches. So we can only divide by prime numbers: 2, 3, 5, 7, 11, 13, 17. Okay, 5 is not a prime number, even though, not 5. 9 is not a prime number, even though a lot of you want to call it a prime number. So keep that in mind. Okay, anytime we're dealing with an even number, I like to just start with a 2 and do as many 2s as possible. So 36 divided by 2 is 18. 18 divided by 2 is 9. 9 is not divisible by 2, and it's not prime. 3 is going to be the next prime number, and 9 divided by 3 is 3. So at the bottom, once you have a prime number, you're done. You don't need to divide that by 3 to get a 1. We don't need to end up with a 1. Once you end up with a prime number at the bottom, you're done. So then we're going to see what kind of pairs we can make. So I see a pair of 2s and a pair of 3s. So I take one number from each of those pairs and multiply it out to get my answer. So 2 times 3 gives me an answer of 6, which is what we know the square root is. Okay, sometimes though, you're not going to be able to get that whole number. You're going to have numbers left over. So I'm going to show you what to do when that happens. So let's look at square root of 50. Okay, square root of 50, I'm going to start with my prime factorization. Okay, 50 divided by 2 is 25. 25 can't be divisible by 2, but it can be divisible by 5, which is a prime number. 25 divided by 5 is 5. Okay, since 5 is prime, I'm done dividing. I'm looking for pairs. So right here, I have a pair of 5s. Anything that pairs up comes outside the radical. Okay, just one number per pair. So meaning I'm not listing a 5 and another 5. Just like up here, I listed a 2 and a 3. I take one representative from each circle. So anything that's circled comes outside. Anything that's a loner that does not have a pair stays inside. Okay, so basically my answer here would be 5 square root of 2. Okay, you can see here that it can be written as 2 times 5, which is 10, times 5 is 50. Those are just my prime factors. Okay, I don't list them back out under the radical like that because I'm able to see from my prime factorization what matches up and how we can reduce it. Okay, we know we could check our work up here. 6 times 6 does get me back to 36. You could do the same thing here. 5 square root of 2 times 5 square root of 2. So I know that 5 times 5 is 25. Whoops, I didn't write my other 2. Okay, square root of 2 times square root of 2 Anytime you have a number under a radical times the same number under the radical, it just equals that whole number. So this is 25 times 2, which does get me back to my 50. So that is a way you could check your work if you're not sure. Okay, let's look at 300. Okay, I'm going to do it as a prime factorization using the birthday cake method. So it is even. I'm going to start with a 2. So 300 divided by 2 is 150. 150 divided by 2 is 75. Okay, 75 can no longer be divisible by 2, but it is divisible by 5, which is a prime number, and that's 15. And then let's say we divide 15 by 3. 15 divided by 3 is 5. 5 is a prime number, so we're done. So I'm looking for anything that pairs up. So I see a pair of 2s, I see a pair of 5s, and then I see a 3 that does not pair up. Okay, so on my radical, 3 stays underneath. I bring a 2 to the outside and a 5 to the outside, and I'm going to multiply those two things together. So we can say that this simplifies to 10 square root of 3. Now, if you recognized that 300 can be written as 3 times 100, this might have been a quicker way for you to do it, because you can take the square root of these numbers individually. And we know that the square root of 100 is 10. So we can take that square root and put it on the outside of our radical and leave the 3 on the inside as something we can't take the square root of. We got the exact same answer as we got using our prime factorization. Okay, so looking at a squared, anytime you have the square root of a squared value, remember these two things cancel out and you just get an A. Okay, if I wanted to check my answer, I could do A times itself, so A times A, and that gets me back to my original value of A squared. Okay, B cubed, so I have B to the third power. So anytime we're dealing with variables, I have B to the third power. If I divide that by B, B cubed divided by B is just B squared. Divided by B is just another B. B squared divided by B is B. Okay, looking for pairs, I have one B that pairs up, so he comes outside the radical. I have one B left over, so he stays inside the radical. All right, let's look at 98 times x to the third power under our radical. So we're taking the square root of 98x cubed. So I'm going to start with my 98. I'm going to divide that by 2, 49. Divide that by 7, and I get 7. So my prime factorization is 2 times 7 times 7. So I have a 7 that pairs up, so it comes outside the radical, and I have a 2 underneath still. Okay, my x cubed, I have x times x times x. So I have one set that pairs up, so I get to bring an x outside, and then I still have one that stays underneath. So I can say that 98x cubed, when I take the square root, is going to be 7x times the square root of 2x. Okay, 16m squared q under our radical. So we know the square root of 16 is 4, so that gets to come outside. Square root of m squared, so I have m times m, that makes a pair. It gets to come outside the radical, and I don't have any m's left inside. And then q does not have a pair, so q gets to stay under the radical. Okay, I want to just look at one last one right here, the square root of 64x to the 8th y squared. So square root of 64 is 8, and then I have x to the 8th power. So you could list them all out, x times 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 x. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4. So on the outside, I have x times x times x times x, because I have 4 pairs, which is going to make x to the 4th power. So I have 8x to the 4th outside my radical, and then I have the square root of y squared. So y times y, that makes one pair. So I have a y. And I'm not going to have anything else left under the radical. Everything else, everything I was able to take the square root of. Okay, you can also think of it as when you're taking the square root, it's the 1/2 power. So you have x to the 8 to the 1/2 power when you take the square root. And remember, a power to a power you multiply. So 8 times 1/2, that means it simplifies to x to the 4th when you take the square root.